Welcome to Maths with Bob. Today we're looking at the cross product of vectors in 3 dimensions. Let's have a look. Where is it? Here it is. Here's the cross product. And basically you can see it basically is just, you're multiplying two vectors together. A times B, it looks like as opposed to the dot product where it's a big dot. That's another way of multiplying vectors together. And that result is a scalar. This result is actually a vector. So A cross B will give you a vector. Okay. Now, the first thing is we're going to have a quick look at geometrically what this means. Okay, geometrically, it's basically over here. It's basically geometrically, you can see here, it's okay. A cross B is equal to length of A times length of B times sine theta times this n hat. N hat is a normal unit vector. Now, so the magnitude, you will see later on, of this particular, basically, because the magnitude of this is 1, obviously, so the magnitude of A cross B is just the length of A, or magnitude of A times the magnitude of B times the sine of the angle in between them. Okay, so just to recap, n hat is in fact the unit normal vector to the plane of A and B, actually. The magnitude of A, or length of A, and B we need here as well. Now the direction is given by what's called the right hand rule. Now what you need to do is you need to point your index finger, okay, this one over here, in the direction of A. Okay, and B, okay, your second finger, you need to point in the direction of B, and some people actually say you just curl your fingers around this way, and basically your thumb over here, okay, your thumb is actually going to point in the direction of A cross B, okay, so it's a vector. And its direction is given by what's called the right hand rule. Okay. Now, geometrically, also, you can say that in fact the, if you like, the length of A sine theta, okay, is this height here. It's actually the height, and if you multiply that by the length of B over here, you'll get the area of this parallelogram. We could use this idea to find areas of triangles, because we're actually going to cut them in half as well. But basically, the magnitude of you can see here, A cross B, is the area of the parallelogram formed by the vectors A and B. Okay, this means that the length of the vector product A cross B is numerically the same as the area of the parallelogram formed by A and B. Okay, so basically the length of A cross B is actually basically the same as the area of that parallelogram. Okay, so what you do is really, if you find this area and you multiply it by that normal vector, you'll get the vector A cross B over here. Okay. Now, you'll see I've actually got A cross B is actually pointing down. Okay, you'll see here, and if you get your right hand out and try and point your index finger in A's direction and B, your second finger, you'll see you'll have to turn your basically hand upside down, and you'll get that the direction of your thumb is downwards in this case. Okay, you might like to try that. Okay, now algebraically, the cross product is a bit of a messy formula. You can see here, this is a messy algebraic formula here. Basically, it's quite a bit of when you have to do a bit of multiplication, cross multiplication, and you'll see here it's a fairly complicated one to remember. That's why we normally would just use this. You can see here, this is the determinant method, which I normally just use actually. Basically, I'll just try and shrink this down a bit. It's basically this bit over here, A cross B. You normally just use the determinant I, J, K, and then the components A1, A2, A3 of a vector A, and underneath you put the components B1, B2, B3 of vector B. Okay, and you basically, obviously, hopefully remember, when you expand out determinants, it goes plus, minus, plus, and this is why we have the plus I, and then you basically cross out the row and column and then have a quick look at what's left. You have a C here, A2, A3, B3, oh sorry, B2, B3, B2, B3, here we are. And then you get minus J, cross out the column and the row, and then you've got what, A1, B1, A3, B3, A1, B1, A3, B3, and you know, okay, you get it down to the 2 by 2, which is quite easily to expand, because the 2 by 2s, you just cross down this way, A2, B3, and you minus cross the other way, A3, B2. Okay, you can see here. But basically, you will need to know how to expand out determinants, really, to work out the cross product. Now, there's a couple of things here. It's very handy, this circle here with I, J, and K in it. And basically, these if you like, this circle will give you the just try to make J over here, but you have a look at I cross J is K, J, say I cross J coming around this way gives you K, J cross K coming around this way gives you I, etc. If you go the other way, you just get the negatives of the results, basically because A cross B is not equal to B cross A, or it's actually equal to the negative of B cross A. Okay, and you'll also note a few things here. I cross I is 0. Okay, basically because the two unit vectors will be parallel and the angle between them will be 0, sine 0 is 0. Okay, anyway, you can work that out, but that's not too bad. So this little circle with an arrow going clockwise is very handy. Okay, I, J, and K. You can put them in any order, but basically, as long as you know you do it I, J, K or J, K, I, because as you go around the circle clockwise, you'll get the next one. It'll be positive when you come back this way, like I cross K coming back this way is negative J. Okay, very handy one. Okay, let's have a look at some examples now. Okay, our first example is it says find the unit vector perpendicular to both the vectors A and B. Now, the first thing is obviously, oops, we're moving things here. Hold on. Okay, so this is the determinant we have to work out here. Okay, let's try to make it a bit bigger. Okay, all right. So this is the one we have to work out here, I, J, K, and we put the vector 2, 4, minus 3, 2, 4, minus 3, 2, 4, minus 3. You can see here, and B. Look over B, 5, minus 3, 2. Okay, down the bottom there. Okay, 5 minus 3, 2. Okay, so this is the determinant you need to work out. Okay, it's not too bad. If you go through and work it all out, it's going to, well, let's see here, it works out to be over here. Well, this one here, minus I minus 19J minus 26K. Now, the length of this is the, okay, this is the, if you can see here, this is the vector A cross B here. Okay, now its unit vector, okay, is just basically you divide this by its length. Okay, so you just get the vector's length, just in 3 dimensions, the square root of minus 1 squared plus square root of, okay, they're all underneath the same square root sign, so it's minus 19 squared plus minus 26 squared equals the square root of 1038. Okay, so this is the this is the length of A cross B, and what you do is you get the vector and divide it by its length to get what's called the unit vector. And you can see here it's roughly about minus 0.03i, minus 0.59j, and about minus 0.81k. So if you actually took the square root of negative 0.03 squared plus minus 0.59 squared plus minus 0.81 squared, you should get length of 1. Okay, so this is the unit vector. Okay, now I did a little bit of verification over here just to show you that you can actually use the dot product quite nicely here to verify that in fact that these two vectors are in fact, if you like, perpendicular, because remember A dot B was what, length of A times the length of B times the cosine of the angle, and the cosine of 90 as you know is 0, so that's why if you go A dot A cross B here, okay, and you get 0, you know that these two are perpendicular, and you can verify it here quite easily as well, that b dot a cross b is actually also 0. Okay, so in fact, this vector here, a cross b, is actually, if you like, perpendicular to both these two vectors here. Okay, and its unit vector you can see here over there. This is the unit vector. Okay. Okay. All right. Let's look at another example. Here's another example that says find the area of the triangle with vertices A, B, and C. So you just form some vectors AB and AC. Okay. Now why would you do that? Well, you're going to use an interesting fact that the area of the triangle is half the area of the actual parallelogram, and the magnitude of the cross product is actually the area of the parallelogram, and hence half the area of the magnitude of the parallelogram is the area of the triangle. Okay, ABC, which is quite a nifty sort of idea here, but basically let's have a quick look how you do it. Okay, that didn't work too well. I'll try that again in a second, but basically you can see here -7 -3 7. Okay, basically you have to first of all form the position vector AB, which is just going to be 6 minus 1, 2 minus 5, and -4 -3. Okay, so you get -7 -3 7 here. Then you form the free vector, if you like, AC, which is, remember, 4 minus 1, which is 5, etc. So you form these two free vectors. Let's see if I can get my circles are not too good at the moment. Okay, so here's the determinant we have to work out. So we need to put these two vectors in, -7 -3 7. Okay, these two vectors over here, A and B. Okay, and these are their components, X, Y, and Z components. You can see X, Y, and Z, X, Y, Z, okay, components. And you work out the determinant. Now the determinant, okay, you're going to have to work this out, but it ends up, you can see here, 41i plus 63j plus 68k. And the length of this, okay, is, you can see here, the square root of 41 squared plus 63 squared plus 68 squared, approximately 101.36, and hence the area of the triangle is about 50.68 units squared. Okay, so that's quite a nifty use of the cross product. Okay, let's go and have a look at GeoGebra and have a quick look at the cross product in GeoGebra. Okay, here we have GeoGebra, and we have a this is a little bit tricky because I've got these two vectors in three-dimensional space. So when I move them, you can see here. Oops. Okay. So let's actually just try and move one of these vectors. And I'll just show you what happens. So if we've got A cross B, so you need your right-hand rule. So if we, it's interesting if you know. Well, I'll just show you. If I've got obviously the sine of the angle actually obviously increases up to 90, then decreases. You can see here the cross product. Okay, now if I try and move one of these vectors to the other side, which is a bit tricky in 3 dimensions because of this plane, but the vector will go in the other direction, and I'll try and move. If I can move one of these. Okay, all right. So I've now moved. I don't know whether you can see I've moved. Yes, the vectors. Now I'll just try and get this a little bit more sensible. Okay, oops. Okay, here we go. Okay, so we now have, you can see in 3 dimensions now you've got u and v. If you try, remember, if you have index finger pointing in direction of u, which is this one over here, and v, so if you actually point u and v, you're going to have to turn your hand upside down so that your thumb will be pointing down. Okay, so that's the A cross B is actually this vector coming down here, actually from underneath. Okay, and you can see here, if I can sort of, if I start moving these ones around a bit, it's a little bit tricky. Okay, because I'm sort of basically these two vectors are lying on this purple plane, and it's sometimes a bit. It's I found it was quite difficult to move the vectors around a little bit in three-dimensional space, and to show you that the actual u cross v over here is actually going to be pointing in the other direction. But it's I'll just let it go for the moment. But thank you for watching. This is the cross product of the two vectors u and v. You can see here I can actually fiddle with these a little bit, but it's just a matter of okay, you can see here if I change the length, obviously I change the magnitude and all of these things as well, but it is quite a sophisticated application here in GeoGebra. But anyway, thank you for watching, and bye for now.